Hello, welcome to Computer Graphics Rendering, and today we're going to talk about real-time rendering. We're going to cover three main topics. The first one is what is rasterization. Secondly, we're going to look at the rendering pipeline. And lastly, we'll take a look at G-buffers, which are used in deferred rendering. So in this series, we've been talking about ray tracing. So compared to ray tracing, essentially rasterization is essentially drawing the geometry rather than doing a bunch of ray intersection tests. So it's a lot more efficient because you essentially can map a triangle to a bunch of pixels a lot quicker than you can shoot rays from a camera and then go through all the objects in a scene and test for intersection or not. So typically the way we do it is our app is running some kind of game, visual simulation or something, and we have a bunch of geometry that we need to process, and once we finish processing that, then we can go ahead and rasterize it. In other words, we turn the triangles into pixels, and after we've done that, when we basically get our image. So in the geometry step, this is where we might use matrices for translation, rotation, scaling. We might want to decide colors for vertices and so on. And then the next step is to take that, which we will call that world position coordinates. We're going from the object location to the object coordinates to world coordinates. And then we want to go from world coordinates into the camera space. So we call that camera space or view space. We want to go into camera coordinates. And then we want to project it, which is going to give us clipping coordinates. And after that is finished, then we can go ahead and turn it over to the rasterization area where we can actually just convert the start drawing pixels. Now, between the geometry and the rasterization, we have the step where we want to project from 3D to 2D. And in order for us to do that, we can go ahead and take our x, y, z coordinates that are the output and divide by z, which is the projection. So sometimes we'll call this a perspective division, and this essentially takes us from 3D coordinates to 2D coordinates. So let's start taking a look at the pipeline. So with the pipeline, we essentially want to take our 3D models and convert them into a final image. And we might have material properties associated, such as texture maps. So we might have some raw images that we need to use. And then in the way that we typically do this is we write a shader, a vertex shader or a fragment shader, so we might have source code. So these are external things that we might have to figure out how to load into our program. And then the second thing that we're trying to do is, well, how do we get this in a usable type of data structure that the GPU wants to use? So, for example, our vertex shaders and fragment shaders, we need to compile those into a shader program, and the images, we want to create a texture object out of it, and the model we need to convert to an array buffer object. In other words, a raw set of data that has all the positions, normals, colors, and so on. So starting from our model, at first we need to convert it into triangles. Now our model might not necessarily be composed out of polygons, or it might be curved surfaces. And so typically we're trying to convert these into triangles because triangles are much easier to deal with on the hardware level, and because of the unique geometric property that triangles are always flat. So we're always trying to convert models into triangles so we can use those, and then we can take those triangles or that information there and store it in an array buffer object. Images are more or less straightforward, just more or less copying the pixels into an array that we can then store on the graphics card. And lastly, the vertex shader and fragment shader, we have to compile and link those. So we'll normally compile each of the vertex shaders and fragment shaders, and then we link those together to form a shader program. Okay, so let's see how this is going to actually be processed when it comes to the GPU. So now we're looking at it from a perspective of the GPU, and we will start with our array buffer object. And what we need to do with this, the first step along the line is the Vertex Shader. And the Vertex Shader is going to allow us to take our raw data that we've imported from our models and be able to turn it into something that can then be drawn on the screen. So we might have some uniforms to go with it. Uniforms are essentially constants that apply to the whole Vertex Shader. These would include the world matrix, camera matrix, projection matrix. We might have some additional information we might need to pass to our Vertex Shader, but these are essentially extra data that can control our Vertex Shader after it's been compiled. After the Vertex Shader, then it goes to the perspective division. In other words, you're going from 3D coordinates to 2D coordinates. And after we have done this, then we can start doing clipping and backface culling. These help reduce the objects so that they're visible. We only want to draw what's actually on the screen. Okay, so not everything that comes out of Vertex Shader is going to be on the screen. The next step is then we convert those. We actually do the rasterization step where we're creating fragments, and fragments are essentially the small parts of the polygon that are in the pixel. Sometimes there's more than one fragment per pixel, and so this is why we don't call this a pixel shader, although more or less fragment shader and pixel shader are synonymous with each other. So after we've got pixels to draw, or fragments, we send it to the fragment shader. And in this step, this is normally where we would incorporate more constants. These could be like material properties and so on, or texture maps. A lot of times this is where the textures come into place. And so the idea here is we want to generate a color. And so after we generate the color and we have the Z position, then we can go ahead and do some extra processing. So we do the Z test here, which is part of the Z buffer algorithm. This allows us to use a separate image to track which point or which fragments is the closest fragment drawn, and this enables us to make sure that objects that are close overdraw those that are far away. And then we can do additional steps like blending, where we might have some transparent objects that are, say, maybe 50% translucent and so on. And after we do these steps, then we finally write the color into the frame buffer, which then has our final image. Okay, so with this process, it is possible that the Vertex Shader or the Fragment Shader are going to be computationally expensive, and it's normally in the Fragment Shader. In other words, we might want to do these complicated lighting calculations, and the Fragment Shader typically can be really big and expensive to compute. And so what we might want to do is come up with a way of optimizing this so that, for one, we don't have so much overdraw, because the depth buffer can be expensive in terms of if you spend a lot of time calculating the light for a fragment, and then it turns out it's just going to get overdrawn in the next once the next fragment comes in, then we wasted a lot of time. So a lot of times we'll use a special process called Deferred Shading, which uses a G buffer. So let's take a look at what a G buffer can do for us. So a G buffer essentially is allowing us to avoid the problem of overdraw when we have expensive shaders, especially fragment shaders. We're doing some fancy lighting and we're just wasting our time. If you think of a 3D object with lots of objects to see, you're going to have a lot of overdraw. So one way to do it is use a G buffer. In other words, we just try and we want to create some images that hold some important information that we might need that doesn't take a lot of time to compute, and then we'll do the lighting. So the process of doing this is that we need to render to a texture map. One way of doing this is to use a frame buffer object, and a frame buffer object allows us to kind of simulate the actual screen or image, the final image we're doing, but instead of storing it in a way that's just going to get sent to the monitor, we store it in a texture map that we can then use as an input to a fragment shader later on. So we basically use two steps. First we draw the G buffer, then we're going to draw basically the whole screen all at once, and then use a separate shader for the lighting calculation. So The G buffer is basically used to save things like the Z coordinate or normals, and we might also want to store extra information like the diffuse color, specular exponent, maybe some other material properties that are just not going to change and don't take a long time to compute. And the way that we do this is, we're going to iterate through the lights in the next section of the shader, and the idea here is we use these values then in that stage where we're guaranteed to not have any overdraw at all, so we can do as many expensive operations as we'd like. Okay, and then we accumulate the results. So we basically say, okay, for all the lights visible for this fragment, let's go ahead and do the lighting calculation, and then we just keep adding on. So the more lights we have, the more we just do a for loop essentially that goes through each light, calculate the result, and add it all together. So we might need to, we want to take a look at how we store these. So essentially, a frame buffer object is just an image, and a lot of times we can take advantage of a higher resolution data type, like a floating point number, 32-bit floating point number, rather than the typical 8-bit colors that we're used to for images. So we essentially can pack things like the normal. We might want the normal. Maybe we have a diffuse roughness value if we're going to use Orinator or something like that. And sometimes, though, that's not enough buffers. So sometimes we are able to actually draw to several frame buffer objects at one time. That way we can store a lot more information. Otherwise, we have to draw the geometry several times in a row to get these extra buffers. So the next one, we might want to store the diffuse colors, so RGB colors, and the maybe the specular roughness value for the material. And sometimes just depends on the hardware, but we could have more. So maybe we want to store the camera vector, so we can do some more calculations. And the little question mark in that last box essentially is for whatever we want. Maybe we have some other material property we want to save. So with these in mind, we're essentially just packing fields. Okay, so remember, these are images. We're thinking red, green, blue, and alpha, but we're not going to say that those have to be red, green, blue, and alpha. We're saying, well, it could be the normal, it could be a roughness value, it could be a vector. So we want to pack the fields, but a lot of times this is dependent on a hardware limit. So perhaps a mobile phone doesn't let you have, or doesn't allow you to easily save 4 buffers at one time, and maybe you're limited to 2 or 1. So, but this is still a much faster way than doing the like a monolithic approach where you have a lot of overdraw. But on the other hand, it depends on the speed of memory as well. So you have to balance how much you use a G buffer versus how long it actually takes your fragment shaders to go. So the faster the GPUs get, sometimes you can get away with not with just simulating a G buffer. So you separate the steps of calculating your normals and so on, and then you do your lighting calculations. And then there are some other approaches where you can kind of divide the screen into smaller areas and render one small chunk at a time. So that's another approach that can use a G buffer. So anyways, let's go ahead and review. We basically talked about rasterization and compared it quickly to ray tracing. And it's also important to note this is very similar to the Reyes architecture that Pixar uses in the RenderMan software. And secondly, we took a look at the rendering pipeline from 2 points of view. The first point of view was what kinds of objects do we need to even use? And then the second thing is, how do those objects get used step by step from just having data to getting an image? And lastly, we took a look at the G buffers, which are a way of which are a component of deferred shading, where we divide the lighting calculations from saving important information about the models, like the normals, colors, and so on, that in order to avoid the problem of too much overdraw when our fragment shaders get a little bit expensive. Well, thank you for watching the video, and adios.